So we finished up to here. 17. Okay. All right. So for those who are here, we are solving by substitution when we have something that requires chain rule to do the derivative of. If we're integrating and we know chain rule has been applied, this is when we do U-Substitution, do that inverse chain rule. So here, now again, you have two separate functions. You have one in the numerator, one in the denominator. You're going to pick the one with a greater degree. So we're going to say that u is equal to x cubed plus x. That means if we take the derivative, du is equal to 3x squared plus 1, which happens to be our numerator. So that means we end up with the integral of 1 over u du. So we replace x cubed plus x with u, and we replace the numerator 3x squared plus 1 with du. I did post the recording earlier this morning, so sorry I didn't get to it yesterday. Kind of ran out of here. All right. Now, what's the integral of 1 over u? Oh, natural log of u. Don't forget it has to be absolute value plus c. And then we put u back in. So natural log of x cubed plus x plus c. All right. So, number 18, again, we have a situation where we have a function, a numerator and denominator. We try to put u in for the more complex function. So that means we're going to use u as equal to 1 plus e to the 2x. Now, if you take the derivative, okay, take the derivative, that's going to give you 2e to the 2x, right? dx. Now, I don't have 2e to the 2x, but I have e to the 2x. So I'm going to say take 1/2 of both sides. And 1/2 du is equal to e to the 2x dx. So again, we're going to replace 1 plus e to the 2x with u, and replace e to the 2x dx with du. So substitution, which again gives us the same integral we had before. We get the natural log of the absolute value of u plus c. In this case, we had natural log of 1 plus e to the 2x plus c. And I didn't forget the 1/2, didn't I? So 1/2.
Where do you put e right on top?
It got replaced with 1/2 du.
How'd you get the 2 into the 2?
Derivative of e to the 2x. You have to do chain rule. Yeah, don't forget the chain rule. All right. 4/14. Now, in this case, what's the more complex function? What was that? Oh, okay, sorry. I didn't forget about function. All right, well, 13. We'll do that one instead. What's the more complex function? Natural log of y. U is equal to the natural log of y, and du is equal to 1 over y dy. Now, we can separate our function as the integral of 1 over y times 1 over the natural log of y, because it is multiplication. We just replace natural log of y with what? U. And we have 1 over y times dy gets replaced with du. So that gives me the natural log of u plus c, which ends up being the natural log of the natural log of y plus c. Now, I'm going to ask this question. If you know it, great. If you don't, it's fine. Why is the outer natural log absolute value, but the inner natural log not?
It is from either.
No matter what.
No matter what it's on.
Yes.
And it's inside, so no matter what.
Mainly because from the original function. The natural log of y is from the original function. And from the original function, the y value would be restricted to being only positive to begin with. But yeah, if it was the case that the natural log of y will always be positive, then we wouldn't really need absolute value, would we? Can you get a negative value outside of natural log? Is there values you plug into natural log that gives you negatives? Yeah. Yeah, there is. Anything between 0 and 1. So in this case, y would have to be greater than 1 to make this work. Yeah, natural log of anything between 0 and 1 would give you a negative value. This is all right. Try 14. 14 is pretty much very, very similar question. So we're going to substitute u in for what? So log of x, which means du is equal to 1 over x dx. So in this case, we do have integral of natural log of x times 1 over x dx, which means we get the integral of u du, which is 1/2 u squared plus c, which then gives me 1/2 natural log of x squared. Let's see.
Yeah, absolute value.
Wouldn't be because it's from the original function. Whenever we do the integral of 1 over u, because my 1 over u does not require itself to be positive, when we do the integral, My u now requires it to be positive. So in order to make sure that happens, I do the absolute value. So it just depends on where it's coming from. If it's coming from a value that wasn't necessarily designated as always positive, you have to make sure it's always positive. All right. Number 19. What do you want to plug u in for? U is equal to 9 minus x squared, which means du is equal to what? Negative 2x dx. We don't have a negative 2x dx, so basically just multiply by a negative 1/2 to cancel that out. So we have negative 1/2 times the integral of 1. Well, let's just write it as u to the negative 1/2 du. I mean, I'll put it on there and then I'll convert. So 1 over the square root of u du, which is negative 1/2 integral of u to the negative 1/2 du. Just so we know where it's coming from. So doing integration means we're going to add 1 and then we get positive 1/2. Divide by the sum, we get a positive 2. So negative 1/2 times 2u to the 1/2 power plus c gives me negative u to the 1/2 plus c. And since u is equal to 9 minus x squared, that is negative 9 minus x squared to the 1/2 power plus c. Right here, x dx got replaced with negative 1/2 du. Now, if you weren't here yesterday, I can only imagine how interesting this is right now. So make sure you watch the video from yesterday. That will greatly help. All right, so here u is equal to 3x plus 1, which means du is equal to 3 dx. Well, now we don't have a 3 dx, so we're going to do 1/3 du is equal to dx. So this becomes the 1/3, the integral of e to the u du, which is 1/3 e to the u plus c, 1/3 e to the 3x plus 1 plus c. And lastly, we're saying u is equal to 1 plus e to the 2x. No, because what happens if we do the derivative of that? We'll still have e to the 2x, right? Do I have e to the 2x? No. So what I'm going to do instead is separate this out as the integral of 1 over e to the x plus e to the 2x over e to the x, which gives me integral of e to the negative x plus e to the x dx. Which I could do this pretty easily. What's the integral of e to the negative x? You have to account for the negative, so we negative e to the negative x. So negative e to the negative x. If you took the derivative of this, you would get e to the negative x, because the negatives would cancel out. And the antiderivative of e to the x is e to the x plus c. So we actually didn't have to use substitution for this one. In fact, we couldn't use substitution for this one. I mean, you could, and it's just unnecessary. So whenever you try U-substitution and when you do the derivative to find, du, and you're left with something that's not in your function, then you cannot do substitution. Okay, we were left with e to the 2x, and there actually we were left with 2e to the 2x. We didn't have another e to the 2x. It was not a word. Now, next page. When doing U-substitution with definite integrals, there's two ways to do this. All right, I'm going to show you both ways on number 23. All right, so pretty much the normal way is to do exactly what we've been doing, and when we're done, plug my function back in. So we're going to integrate from 1 to 5, but I don't want this. I'm going to say u is equal to 2x plus 1, which means du is equal to 2 dx. I don't have a 2 dx.
Fine.
Yeah. Sure, minus 1. So 1/2 du is equal to dx. So 1/2 of the square root of u du. Right. Now again, if I want to write this as 1/2 from 1 to 5 of u to the 1/2 du, I can. If I add 1, it gives me 3/2. Dividing by 3/2 gives me 1/2 times 2/3 u to the 3/2 du. Now that's going to give me, run out of room here, 1/3 u to the 3/2. Now I don't have to worry about c. I don't need the du, sorry. I don't have to worry about c because I actually have bounds here, 1 to 5. So from 1 to 5. Now this is where where we differentiate a little bit. One method is to just replace my u with my function. So 1/3 of 2x minus 1 to the 3/2 from 1 to 5. And then just plug them in. If I plug in 5, I get 10 minus 1, 9. Okay, 3/2, 9 to the 3/2 power is 27. 1/3 of 27 is 9. I plug in 1, I get 1. That just gives me 1/3. So I end up with 26 over 3. Or
We think our equation for the we go to x minus x and we find the x and receive.
What?
When
take your when you take your value, you mean your bounds? Yes. So the other way, is what he said. Notice that we replaced my u with my function. And what did we do to the bounds? We plugged it into the function and then did the 3/2 power. So what we can do is once we replaced u with 2x plus 1, we can also run our bounds through our function. If we do that, we don't have to plug our function back in. So if we say that u is equal to 2x plus 1, all right, then my bounds from 1 to 5, if I run them to the function, okay, become 2 times 5 plus 1, and 2 times, I say plus 1, I'm writing that. It's minus 1. So minus 1. 2 times 1 minus 1. We get my bounds are 9 to, well, still 1. So now when I do the integral from 1 to 9 of u to the 1/2,
Shouldn't that be 2/6 instead of 1/3 because it's 1/2 times 2/3?
no, because you cancel the 2's out.
6.
Oh yeah.
2/6 is 1/3. All right. So now we have 1/2. Now my bounds go from 1 to 9. So the idea is to just run your bounds through your function so you don't have to plug your function back in. So we get 1/2 times 2/3 of u to the 3 halves from 1 to 9, which gives me 1/3 u to the 3 halves from 1 to 9, and then plug them in. That's the same thing. Plug in 9, I get 27. That's 9 minus plug in 1, I get 1/3. We still get 26 over 3. So it just depends on really how you want to do it. Do you feel more comfortable plugging your function back in and then not having to mess with the bounds? Or do you think it's easier to run the bounds through your substitution as well? Here's the thing. I don't care how you do it. Okay, no one really cares how you do it. You have two choices, you pick your favorite. Okay, you'll not see on a test, do it this way. Okay. So, yeah. So it just depends on how you feel. All right. I kind of prefer to run the bounds through it just because I don't have to do the plug the function back in since I'm already replacing the function with u. So that's probably what I'm going to do. Okay. So here, if u is equal to x squared plus 2, du is equal to 2x dx, which means I don't have a 2x, I have an x dx. I don't have a 2x dx. So 1/2 du equals x dx. So my new bounds, if I plug my bounds through, 1 squared plus 2 is 3. 4 squared is 16 plus 2 is 18. Right? 1/2 of 1 over u du. So, again, rule 1 over u is 1/2 of natural log absolute value of u. Now, in this case, I don't need the absolute value. Why do I not need the absolute value? Yeah, my bounds are all positive. So from 3 to 18. So you get 1/2 natural log of 18 minus 1/2 natural log of 3. And I'm just going to leave it like that. I mean, you can, by the way, can you simplify this actually? Do you remember your logarithm rules?
No.
1/2 of natural log of 18 minus natural log of 3 becomes 1/2 natural log of 18 over 3. And you can bring the 1/2 as a power, yes. If you really wanted to write. Oh, wait, yeah, because 18 over 3 is still reducible. I'm not done yet. So I get 1/2 the natural log of 6 or the natural log of the square root of 6. There you go. I don't know what's easier to do. 1/2 natural log of 6 or natural log of square root of 6. Honestly, I think it should be easy to leave it as 1/2 natural log of 6. Honestly, I wouldn't care which one you left it at. I would want you to simplify it to the natural log of 6, but that's about it. So, all right. Now, we do know that the, oh, wow, this is interesting. There might be two ways to do this. Is there two ways to do this? What's the derivative of tangent squared, tangent x? Secant squared x, right? Okay. What's the derivative of secant x? Tangent x, secant x. So we can either replace u with tangent x, because the derivative of that is secant squared x, right? And that would go away. Or if we wrote this as tangent 2x secant 2x times secant 2x, if we say u is equal to secant 2x, the derivative of that is tangent x secant 2x. So tangent 2x secant 2x. So we have a choice here. That's interesting. Which would you rather do? What do you think is easier? Yeah, let's just leave as tangent. You don't need that. So we'll say u is equal to tangent x, 2x. So du in that case would be 2 secant squared 2x. And we don't have a 2 there, so we do have to bring the 2 out front. So 1/2 du is equal to secant squared 2x dx. All right. Now again, running the bounds through the function, we're going to say u of 0 means tangent of 0. What's tangent of 0? I think it's 0, right?
Yeah, it's 0.
All right. And then u of pi over 8. Now that's tangent of 2 times pi over 8. So it gives you tangent of 2 times pi over 8. So it's pi over 4. What's tangent of pi over 4? It is 1. So now we're going to integrate from 0 to 1 of, well, 1/2 u du. That's a lot easier too. So that gives me 1/2 times 1/2 of u squared from 0 to 1. So 1/4 u squared from 0 to 1. 0, 1 will give me 1. So we just end up with 1/4. It's nice. Fairly complex question, made so much easier through substitution. How we doing? Doing great. Awesome. Good job. All right. So number 26. U is equal to e to the x squared. What is... No, 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 no. Why would that not work? What's the derivative of e to the x squared? 2x e to the x squared. We don't have another e to the x squared there. So we're going to just say u is equal to the exponent. So u is equal to x squared, which means du is equal to 2x dx. Now, do I have a 2x dx? Multiply by 3/2. So 3/2 du equals 3/2 2x dx, which again, we'll just get rid of the 2 there. So I do have a 3x dx. I got rid of that. Now I will go ahead and just run this through my bounds. What is u to the 0 power? What is 0 squared? 0. What is u to the square root of the natural log of 4? What is that squared? Natural log of 4. So I'm just going to integrate from 0 to the natural log of 4 of 3/2 of e to the u du, which is real nice, because it's 3/2 of e to the u from 0 to natural log of 4. Natural log of 4, if I plugged it in, I would just get 4, right? Because that would just cancel out the e. Wasn't e to the 0 power? 1, so 3/2 times 3 is 9/2. All right, that is it for the notes. Tomorrow, or whatever day we meet again, depending on the situation, we will be dealing with some really fun stuff. Remember doing inverse trig functions and derivatives inverse trig functions? We're going to do this backwards now. And it gets worse.
I believe it can always
Yeah.
work.
It gets worse because In order to set it up, we have to complete the square.
Oh.
Honestly,
Wow.
Yeah.
no, I really like math. Go back to that.
So inverse trig, long division, and completing the square. So we will do some long division. I mean, long polynomial division.
No.
Algebra 2. Did you do it in pre-cal? Maybe a little bit in pre-cal. And you can, I mean, most of the time you can probably do synthetic division, but not everything can be done through synthetic division. Did you know you guys can do synthetic division with complex roots?
What?
You can do synthetic division with complex roots.
No.
You can.
Without to lock in, I have to help with
Yeah.
it.
Yeah, I was such a nerd in high school, not, as compared to now. Um, my high school algebra 2 teacher did not think you can do synthetic division with complex numbers. So that showed him you could.
Weird.
It is odd to me that, especially when high school, that having a math teacher not want to learn more math. I always want to learn more math. One of the best college experience I've had was getting my master's. All I did was math classes. That was it. It was awesome. So I'd not have more fun. Now I tell you, there was one class that was pretty rough. Partial differential equations. That was a rough class. But he was just wasn't a very good teacher.
You somebody called it. And did you what word before? Yeah. No, I need to use it.
All right, there is an assignment on Delta Math. If you want to get started.
I will see you. You get that. You don't have to do it. Bird. Mr. Name's boss is
Oh, no.
we're good.
Okay.
The five fifty, I think is so bad. What maybe fun. Oh, really? We can get these in. What? I really not this numbers. Let's see. Nice. The question. It's not. Because it makes sense. This, I get the phone. Wow. It makes yeah, oh, pushy. It's not like it was with that. No, with that. No, it was on.
Well, my system isn't any less. Well, that's good.
You what are you doing already? I'm not the leader.
So bad. My mom. Right. Well,
Oh, so you're paying for this. You feel
and then all the money.
There we go. So, another class. Let's see. It's recording.